Okay, so let's have a look at exam one. All right, first things first, we've got a derivative and it's a quotient rule. Quotient rule's on your formula sheet. Simplify, or you could do the division first, which is what I did, I think. So two ways, I divided both terms by e to the x, so it gives me a 2e to the x. 1 over e to the x is e to the minus x. Differentiate those terms, I end up with a 2e to the x plus e to the minus x. If you go through a quotient rule process, because you don't notice a division or simplification, derivative of e to the 2x is 2e to the 2x. It gives me a 4 out the front times the derivative of the bottom, e to the x, minus derivative of the bottom, which is e to the x, times the top function, which is 2e to the 2x minus 1, over bottom function squared. So e to the x is a common term out the front of all of those. So I get 4e to the 2x. So I guess that e to the x and that e to the x are coming out the front. So it leaves me with the 4e to the 2x, this 4e to the 2x, and this 2e to the 2x minus 1. The minus sign is getting multiplied into both, so it becomes a plus 1. So that's the mistake you're going to make. 4e to the 2x minus 2e to the 2x just leaves me with a 2e to the 2x plus 1. That e to the x here now cancels out with the 2x to make it just a single e to the x. And if I do my division, I'm going to end up back there again. All right, so both methods are fine. And in fact, that would be a fine answer as well. Second one, f dash to the pi on 3, product rule, derivative of the first function, times the second function, derivative of the second function times the first function. All right, so don't forget the derivative of cos is minus sine, or -3. And from that point, instead of trying to simplify, just put your pi on 3 in. So we get 2 times pi on 3. 3 times pi on 3 is equal to pi. 3 times pi on 3 all squared is pi squared on 9. And sine times 3 pi on 3, which is just pi again. Sine of pi is 0, so that second term can just go. And I end up with 2 pi on 3 times cos of pi, which is -1, -2 pi on 3. And then again, another sort of typical early question is we've got a derivative, we now need to find the original function. So just be careful of notation, I don't like it if we don't put our integral in dx sign. So the antiderivative of 2x squared minus x squared minus x to the -2/3 on 4. So I like to write everything in the power. So add 1 to the power and divide. -2 on 3 plus 1 is 1/3. Now, 1 divided by 1/3 is 3. So that's 3 goes up. That's really where the third comes from. And I've still got my quarter there, plus c. A lot of us forget the plus c, and hence we don't go on and get the rest of the problem. Substitute your point in. So at x equal to 1, y equals -7 on 4. There's my -7 on 4. Just pop 1 into everything. Get common fraction, so 12. So I like to get that as soon as I can. So -21 on 12, 8 on 12, and 9 on 12. Group everything together, we get c is -20 on 12. Divide both of those by 4, we get a -5 on 3. All right, so just make sure you rewrite the question. Rewrite your answer at the end of each question. All right, evaluate the integral of those two expressions. So I've just split it up there. So the antiderivative of 1 over x plus √3, it's a log function. Natural log of x plus √3 between 7 and 2. Substitute 7 in, substitute 2 in. It's a subtraction. So I was happy enough just to leave it in that form there. There was no instruction about, rationalizing the denominator or anything like that. So I just left it there. Same for the second one. Natural log of x minus √3 is my derivative or antiderivative. Between 7 and 2 again, so I get 7 minus √3, subtract natural log of 2 minus √3, minus in between, so we do a division. So again, I was happy enough to leave it in that form. Part B, show that a half of that equals x over x squared minus 3. So we've got two separate fractions here into one, so we're going to have to sort of cross multiply here to get a common denominator, which is what we've done. So the sort of x plus 3 there, I've multiplied across the top left. the x minus 3 there, I've multiplied across to the top right, and then we multiply the denominators together because that's how we would do our fractions. And if you forget, just do a little, come to the right hand side, just do a little 1/3. I hate it when I write in that big fat pen. 1/3 plus 1/4 is equal to, 4 times 1 plus 3 times 1 over 4 times 3. That's what we're doing. So what happens? What happens here? So x minus root 3, x plus root 3 is x squared minus 3, difference of squares. And x plus x is 2x, root 3 minus root 3 is 0. So I get my 2x over x squared minus 3. If I multiply that by a half, I'll end up with x over x squared minus 3, which is what I need to do. All right, now using these answers, evaluate the integral of x over x squared minus 3. So I know that the integral of x over x squared minus 3, that expression there, in fact we'll use it in red, this expression here in red, go up to b, is equal to that expression. We just showed that. So I'm going to put the half out the front, and I've got that expression there. And that expression there from part A, if I work out the antiderivative, is the two different log rules. So it all leads me to having a half of natural log of 7 plus root 3 over 2 plus root 3 plus natural log of 7 minus root 3 over 2 minus root 3. Because the integral was evaluated between 7 and 2 already. So I'm adding two logs together. So I'm going to multiply the two together. So I have a difference of squares on the top, difference of squares on the bottom. So 7 squared minus root 3 squared, which is 49 minus 3. And on the bottom, I've got 2 squared minus root 3 squared, which is 4 minus 3. So I get 46 on 1. So a half natural log of 46 on 1, which is the answer I'm looking for. All right. Function has a rule, natural log of, state the maximal domain. So quick graph sketch. It's the natural log function 3 units to the right, isn't it? So it's sort of like that. And we've got our asymptote, instead of being at 0, that's at x equal to 3. Plus 2, and everything's been shifted up 2 units. So it doesn't change a hell of a lot. So my domain is still 3 to infinity, not including 3, and the range is from 2 to infinity. Find the equation of the tangent to the graph at 4, 2, the tangent line at 4, 2. I don't know, maybe something like that. We know the gradient, we need the gradient at 4, so the derivative of natural log of x minus 3 is 1 over x minus 3. At x equal to 4, the derivative would be 1. So that's the gradient of my tangent line. So I've just used y minus y1 equals mx minus x1. Obviously we can use y equals mx plus c. The y value is 2 equals 1 times x, which is 4 plus c. So c equals -2. Oops, -2. And so we get our x minus 2 the same. On the axis on page 7, sketch the graph of the function labeling asymptotes with the also draw the tangent of the graph. It asks us for the graph of the function, label asymptotes, and draw the, we had to do that anyway. So there's a more specific, detailed version. All right, so we've got our asymptote. Didn't ask us for intercepts, so I didn't worry about. There's my tangent line at 4, 2. I guess given that we knew that tangent has to be at 4, 2, because that's what we were told. So you have to have a certain amount of accuracy for that. All right, for -3 to 2 to infinity, h of x is equal to, find the values of x such that h of x all squared is equal to 1. So I've just got to square that whole function. So it's a little bit messy algebraically. And it's probably a nicer way to do it if I think about it. Anyway, first term squared, let's grab it. First term squared is just 2x plus 3 minus 2 times AB, first term times the second term, plus third term squared, which is 4. So if I group my bits and pieces together, 2x plus 7, I've got a minus 1 there. I can take everything to the right-hand side, which is what I've done. I divided everything by the negative sign to make those positive. So I get to this line here, and then I thought, well, let's get rid of that square root sign, so I've squared everything. So that's all that is. I've just squared both sides. So the key is to make sure you square the 4 to get 16. The square root of 2x plus 3 is just 2x plus 3 if I square it. Right-hand side, perfect. If I square it, first term squared, 36 minus 2 times a times b plus b squared, which is 4x squared. And now I can just group everything together again. And then I get left with a quadratic, divide by 4, minus 2x minus 3. I get x equal to 3 and negative 1. Quick check to make sure there's no reason why x can't be 3 or negative 1. And in fact, it can't be negative 1, can it? All right, because negative 1 is outside the domain, therefore x has to equal 3. I don't know if I picked that up the first time. So, part B, find the domain and rule of the inverse function. So again, let's rewrite it. Y equals square root of 2x plus 3. X equals, bring the 2 across, square both sides. Take the 3 and the 2 back. I get y equals there. So that's the hack work now. Attention to detail. H inverse of x is equal to a half of x plus 2 all squared minus 3 on 2. The domain of the inverse is the range of the original. And the range is just that's my square root function, isn't it? Square root function, which might have been shifted left or right, left in this case and down 2 units. So maybe something like that, who knows? But either way, it's down to negative 2. So there's my negative 2 to positive infinity, and the domain is from negative 3 on 2. Sorry, the range is from negative 3 on 2 to infinity. All right, so for 3 marks, rule, domain, range. In fact, we didn't need the range, did we? It just said find the domain. So why give extra information if you don't need to? Just to toss the coin. Fair, we need to observe a head on the first 2 tosses. That she did observe a head. She observes a total of either 4 or 5 heads. So she's tossed the coin 5 times, and the first 2 tosses were heads. All right, which means on the remaining 3 tosses, I need to see 2 or 3 heads. So I guess I thought that was the easiest way to approach this is from a conditional sense. So I'm going to turn it now into a trial of 3, probability of success a half, and having 2 or 3 successes. So my rule, 3C2, 3 trials, 2 successes, a half to the 2 times a half, plus 3C3, 3 successes, 0 failures we could probably put in. So a half squared is a quarter times a half is an 8, 3C2 is 3, 3C3 is 1, 1 on 2 cubed is an 8, add them together we get 4/8, which is a half. Okay, so that's a typical sort of problem. All right, Albin thinks that Jacinta's coin is not actually fair and tosses it 18 times and gets 12 heads from 18 tosses. The sample, based on this sample, find the approximate 90% confidence interval. With the user Z value of 33 on 20. So we know the confidence interval is mu minus Z square root standard deviation, isn't it? So we need a standard deviation. The standard deviation is given by rule on the formula sheet. I know because I had to look it up. P times 1 minus P on N, so 2/3 times 1/3. And despite your reservations, if we have this in a tech-free, the values will come out nicely. So we end up with the square root of 1 on 81, which is of course 1/9. So you should get reasonable values in through here in a tech-free scenario. Okay. So my confidence interval is P hat minus Z theta Z sigma, P hat plus Z sigma. So P hat is the sample mean, yeah, the expected value of the sample. So that's 2/3 minus Z, which we've got is 33 on 20 times 1/9. So what have I done there? I've decided to get a common 3 there. 9 into 3 is 3 times. 3 into 33 is 11 times. So that should be an 11 there. It's a dodgy looking 11. And so I end up with 2/3 minus 11 on 60, 2/3 plus 11 on 60, get a common denominator, 29 on 60, 51 on 60, or 17 on 20. Okay, so there's no doubting, you've just got to be a little bit tidy with your fraction work, all right? Shaded region below is bounded by the vertical axis of the graph function. There's sine pi x. The original line segment meets the graph at x equal to a, where a is some value between 1 and 3 on 2. So you can see that a somewhere between 1 and 3 on 2. B, the area of the shaded region. Show that a of a, so the area in terms of a is given by that function there. So if I want to know the area of the function, okay, I've got the top function in red, sine pi x. Now at that point there, that's the y value at x equal to a. At x equal to a, y is equal to sine a pi. So that's the line y equals sine a pi, which is where this expression comes from. And the key thing to remember there when I take my antiderivative, the antiderivative of sine pi is 1 on k cos pi x, absolutely. But this expression here is a constant. There's no x in there. It's just a value. If a is equal to half, it would be sine of pi on 2. If a is equal to, a third, it's sine pi on 3. So this is just a number. So the antiderivative of a number just has an x value, x pronumeral added to it. I now want to evaluate this thing between a and 0. Put an a in, negative 1 on pi cos a pi minus the a is for the x, a sine pi of a pi, subtract in brackets, negative 1 cos of 0. If I put 0 in for x, I get a 0 at the back. If I multiply the negative 1 on pi through, I get negative 1 on pi cos of a pi. I'm sorry, I'm not multiplying that through at all. It's just there multiplying the cos. Negative a sine a pi is just that. Minus 1 is a plus 1 on pi. So if I bring that plus 1 on pi out to the front, I get those 3 terms still, which are the 3 terms there. All right, so the trick really is just paying particular attention and realizing that this thing here is a constant. Okay, so we're not turning it into a cos and doing 1 on a and all those things because there's actually no x variable in that expression. Determine the range of the values of a. Well, we know that a is bound between 1 and 3 on 2, and I want to know the range of the function there. Okay, so if I substitute 1 in, I'm going to end up with 2 on pi. And if I substitute 3 on 2 in, I'm going to get 2 plus 3 on 2 pi, which gives me a nice little range. All right. Expressed in terms of a of theta for a specific value of a, the area bound by the vertical axis, the graph, and the horizontal axis. So I need to get, so first things first, I want to know the area bound between the vertical axis and the graph of that and the horizontal axis in terms of that. So let's concentrate on what we're looking to evaluate, which is this expression. So we end up with, where does 2 sine pi plus root 3 equals 0? We get 4 pi on 3 and 0. So The area itself is between 0 and 4 pi on 3. The 2 is there because we've got a 2 there, okay? So this is just my function. That's what I want to work out. So how can I manipulate that function? All right. So that's the equivalent of keeping in mind what a of theta is down here in blue. It's two terms, sine pi x, sine a pi. So root 3 on 2, well, that's the same as sine 4 pi on 3, yeah? So, sorry, positive root 3 on 2 is minus sine 4 pi on 3, right? And I reckon that's the leap. That's the leap there, because now I've got this thing here looking a lot like the function that we're trying to make it be in terms of. And in fact, this expression here, all of that expression here, that is in itself a of a, if you like. That's the function. Yeah. So I can write that left-hand side as simply 2a if in fact a is equal to 4/3, right, which it is because that's my limit of integration. Yeah, so that's my integral. Hence or otherwise find the area. Well, we know that the area is in fact given by 2a at 4 on 3. So a of 4 on 3 times 2 will give you the area I'm looking for. And so then it was just paying, yellow is a bad colour to use probably. It's just substituting 4 on 3 into the function that I've got. And just being careful. Cos of 4 pi on 3 is in the negative quadrant for cos of pi on 3, which is a half, so I get negative a half. Sine of 4 pi on 3 is root 3 on 2, negative, so the negative becomes a positive. And then we just got to multiply and group some terms together. Yeah, just be careful with your algebra. That should be the expression that we end up with. That was a tough question. Question 8. Standard die roll 50 times, random variable binomial distribution. Write down an expression for W where K is equal to 0 to 50 successes. So it's exactly that. So 50 trials, K successes, 1 on 6 to the power of K, which makes 5 on 6 to the power of 50 minus K. Show that W equal to K plus 1 over W equal to K. Those probabilities can be simplified as. Right, so if W is equal to K plus 1, my rule becomes, and I'll use red for the top, so 50 trials, K plus 1 successes, 1/6 to the K plus 1, 5/6 to the 50 minus K plus 1, yeah? Over K successes, 50 trials, K successes, 1/6 to the K, 5/6 to the 50 minus K. So if you like, there's our first statement. So then what I've done is just, we've got our 1/6 to the K plus 1 on the numerator, 1/6 to the K, they cancel to leave me 1/6. Now, if I maybe come over here a little bit to the left, 5/6 to the 50 minus K plus 1 is equal to 50 minus K minus 1, which is 49 minus K, isn't it? Yeah. So I've got 50 minus K on the bottom, 49 minus K on the top. So that expression is 49 minus K, which means I've got one extra 5/6 on the bottom, which is what that expression is. Yeah, so what I've done there is I've decided to, well, let's just simplify in yellow, sir. let's just simplify these expressions, okay, to these. I've got a 1/6 times 5/6 to the minus 1, which is 1/6 over 5/6. All right. What about our 50? Let's now come and have a look at these two expressions over on the right. All right, 50 over k, 50 choose k plus 1, or 50 ck. So keep colouring these things in, all right? Again, we'll turn that into green. The green one is 50 factorial over k plus 1 factorial, 50 minus k plus 1 factorial. The denominator, 50 ck, is 50 factorial over k factorial, 50 minus k factorial. So turn the bottom one upside down and multiply the top one. Let's have a look at what we can do there. So I've got a 50 factorial there with a 50 factorial there, that's fine. It's these expressions here, isn't it? So I've got k plus 1 factorial, I've come to the top here, k plus 1 factorial times 50 minus k minus 1, which is 49 minus k factorial. Yeah. So that's on the bottom. On the top, I've got from the yellow section, k factorial over 50 minus k factorial. So that 50 minus k factorial, that's the same as 50 times 49 minus k factorial. Because it's just 50 times 49 times 48 times 40, just reducing by 1. So that's why those two terms can go. Yeah. And in the same way, this k plus 1 here could be written as k times, it could be written as k plus 1 times k factorial, which means those k factorials can go. So look, it's not the most straightforward of simplifications, but in short, I end up with a 50 minus k on the top, a k plus 1 on the bottom, times 1/6 over 5/6. So if we flip our fraction upside down, we end up with a 5 in the denominator, I should say. And so we get the expression that they were looking for. All right. We're at the back end of the paper, so they're not meant to be easy. And I think the algebra on that's a little bit tricky. Hence or otherwise, find the value of k for which the probability of W equal to k is the greatest. Yeah, so if we think about, I guess, the hence part of that statement, in other words, they're saying, can we use this ratio? Can we use the ratio of 50 minus k over 5k plus 1 somehow? So if you think of numbers as they go up or go down, if my numbers increase, say 5, 6, 7, if I work out the ratio of the next number in the sequence over the previous, I'll get 6 over 5, 7 over 6, 8 over 7, yeah? And they're all greater than 1. The moment the ratio is equal to 1, it means the numbers are the same. If the next number goes down, okay, say then if the next number in the sequence is, instead of it being 9, it's 6, I'll end up with 6 over 8, and that would be a sequence less than 1. So if the ratio is equal to 1, that means I've peaked. Yeah, so it's plus 1. If the ratio is positive for each successive number, that means it's increasing as we go. As soon as it equals 1, it means that the numbers didn't increase anymore. And if it's less than 1, it means the numbers are decreasing. So that expression there 50 minus k over 5k plus 5 is the ratio, and I need that equal to 1. So if that is equal to 1, that means my ratios have stopped increasing. So if I solve that expression equal to 1, I get 15 on 2, which is 7.5. So it's somewhere between 7 and 8, isn't it? So if I check my numbers, if I put k equal to 7, the ratio is 43 on 70, so it's increasing. And if I put k equal to 8, the ratio is 42 on 45, which becomes decreasing. So it stops increasing. So at k equal to 8, that's going to be the highest value of w equal to k. All right.